So today let us talk more about conservative forces and the corresponding potential energy that they create. Yes, so while we do that, we will start with the basic definition of potential energy that we have studied in the previous topics, which is change in potential energy. Delta U is negative of the work done by the conservative forces because of which the potential energy is defined. And do we understand that from the basic definition of work done by any force, we can write work done by the conservative force as integral of F dot dr, where F is our conservative force which is doing the work, and dot product with the dr. This gives us the work done by the conservative force. Since there is a minus sign, we will put that minus sign over here, and since we are talking about change in potential energy as the system moves from state 1, let us say, to the state 2, can we say we can correspondingly put the limits of integration here on the right hand side from R1, let us say, to R2 when the system is in a state R1, and from there when it moves to the state R2, the corresponding work done will be integral of F dot dr from R1 to R2. So, this will be the work done by the conservative force. Negative of that gives us the change in potential energy, right. So, this is our defining equation for change in potential energy. See that this is an integral equation, we have an integration over here. We also know that integration is something that is opposite of differentiation, right. So, what will happen if I try to differentiate this whole equation on both the sides? Delta U will come down to du, a very small change in potential energy. Du is equal to, understand that when we try to differentiate this expression, the differentiation will cancel out the integral and we will be left with only minus of F dot dr. This is what we will be left with. So, du is equal to minus F dot dr. A very small change in the potential energy is a small work done. I hope you all understand F dot dr is nothing but dw, the small work done by the conservative force, right. So, it makes sense when we write this equation also. In fact, it is from this equation, when we integrate both the sides over here, we can obtain the above equation back, right. The small, as sum of the small changes in the potential energy will give us the total change in the potential energy delta U, and on the right hand side we will have an integral of F dot dr, right. So, it is coming from the basic definitions itself. Now, can we say that this equation can further be modified and can be written as du by dr as minus of the force F? What we have done is we have just taken this dr down here in the denominator with du. We shall see that this can be done. In fact, physically it has a certain significance. What do we get from here further? We get F is equal to minus of du by dr. Now, this is a special type of equation. What is this equation? This equation says that we can obtain the force acting on the body F if we know its potential energy function and if we can differentiate it with respect to the radius vector r. In fact, this is not as simple an equation as it looks to be, because if you see carefully, the term u here is a scalar term. Potential energy, we all know, is a scalar quantity, whereas on the left hand side we have a vector. Force is a vector. So, by doing some operation on a scalar quantity, we are getting a vector quantity. How is that so? So, we need to understand that when we open this equation and get it in its detailed form, the form of this equation will actually be like this. F is equal to, the vector F is equal to minus of, we are differentiating the potential energy function with respect to the vector r, which when we split along the 3 mutually perpendicular directions, we can write it as del u by del x into I cap plus del u by del y into j cap plus del u by del z into k cap. This is essentially the function that we are writing here as simply du by dr. Now, what is this term? What is del u by del x? Del u by del x is the derivative or the differentiation of the function u with respect to x, considering x as the variable, And since we know that in general u could be a function of all the three expressions x, y and z, when I differentiate it with respect to x, I assume that x and y, both the other variables, are not actually variables, they are constants. So this particular term here that I have written here is the derivative of u with respect to x considering y and z constants. So this is a special type of differentiation where we consider the other variables to be constant for that particular differentiation, and it is called as a partial differentiation. And just to denote partial differentiation, this d that we generally use, du by dr, we replace it with the new letter del, we call it del. So d is replaced by del, du becomes del u. The meaning, the operation as such does not change, but since there is a small condition that we are applying along with it, that when I differentiate u with respect to x, I am at the same time considering y and z constants. So it is because of this condition that I am changing the du by a del u. Okay, so del u by del x is then called the partial differentiation of u with respect to x. What do we mean by partial differentiation? Means we are differentiating u only with respect to x and considering y and z constants at the same time. Similarly, here the second term where I have written del u by del y, this is the partial differentiation of u with respect to y. That means we differentiate u with respect to y considering the other two variables x and z constants. And the third term, del u by del z, is the partial differentiation of u with respect to z considering x and y constants. So see that this is equation essentially is giving us three terms, the three values, the three components of force, the x component, the y component and the z component. In fact, do you understand that's the vector f, if I write it in its vector form, the component form, fxi cap plus fyj cap plus fz k cap, we know that this is in general how we write the vector f. If I compare this equation with this particular equation here, can we write from here, comparing the terms, can we write fx should come out to be minus of del u by del x, fy should come out to be minus of del u by del y, and similarly fz should be minus of del u by del z, right? So these expressions then are important because they help us find out all the three components of f just by using one potential energy function u. We just have to differentiate u with three different variables one at a time and find out the three components of the force f. So in that sense, this equation is an important one. We use this into questions directly. I'll just give you an example maybe to see how we work with this. So for example, we already know that the potential energy of a spring is given by half kx squared, right? From this potential energy function of a spring, can we find out the force that a spring exerts? F, which by definition should be minus of d. Here I can write du by dx because I see that potential energy is only a function of x. It's not a function of any other variable. K is a constant here, the spring constant. So it's only a function of x and I have to just differentiate with respect to x. That's why I can write it as du by dx itself, although I could have written it as minus of del u by del x also, so that if there is any other variable, I'll just consider that to be a constant while differentiating. Now when we do minus of du by dx over here, see what do we get? So this implies f is equal to minus of d by dx of, what is the function u? It's half kx squared, and now we differentiate it with respect to x. So when we differentiate it, do you see that we will get minus of half k being constant will remain as it is, and the differentiation of x squared with respect to x will be 2x, right? And see that we are getting the answer here as minus of kx, which we know indeed is this expression for the spring force. The spring force is given by minus of kx. Don't we know this already? Yeah. So do we see this is kind of a verification that we are getting that this formula works for us. Let's take one more example here. Let's say the potential energy function at any given space because of some force is given by x, y, z, just x, y, z, okay, and we are supposed to find out the corresponding force here. So, can we say by definition, if force is given by minus of du by dr, which we can also write as minus of del u by del x I cap plus del u by del y j cap plus del u by del z k cap, we know that this means that fx, the x component of the force, will be minus of del u by del x, which will be, in this case, will be del by del x of, what is the potential function? It is x, y, z. So, what are we supposed to do? We are supposed to differentiate this function with respect to x, considering y and z constants. So, do you see what will happen? Minus sign will remain as it is, y and z being constants will come out of the differential operator, and differentiation of x with respect to x will be 1. So, we will just have minus y into z as our component of f along the x direction. Then fy, the component of force along the y direction on the same lines, will be minus of del u by del y, and we just solve it the same way. So, we differentiate the function x, y, z with respect to y, considering x and z constants. So, minus sign and x and z, because they are constants, will come out, and differentiation of y with respect to y will be a 1. So, just x into z we are left with, minus xz. Similarly, fz, which is minus of del u by del z, will be minus of del by del z of x by z. Once again, x and y this time are constants, we differentiate with respect to z, differentiation of z with respect to z will be 1. So, we are only left with minus xy. So, these are the three components of the force that we were looking for, and now we can write the net force F as minus yz I cap minus xz g cap minus xy k cap. So, this is how you can get your force vector, all the three components of the force vector, by using just one potential energy function. Okay, so, this is how this expression works. Next thing that we can talk about here is, as we are discussing the relationship between the force and the potential energy, there is the next thing that comes in here is types of equilibrium that we can have corresponding to different types or different values of potential energy that we get for a given force. Types of equilibriums. Let us understand this. What is equilibrium? We say that equilibrium is the state where the net force acting on a system is 0, right? Now, from the potential energy thing, we know that net force can also be written as minus of du by dr. So, can we say if the net force is 0, this implies minus of du by dr is also 0? What is this expression? This expression tells you that du by dr is coming out to be 0 at equilibrium. Du by dr, do you all understand? This is like the differentiation of the potential energy function. If that is 0, can we say that this means that u should either be a minimum or maximum or a constant at this particular time when the force is 0? Because we know from the mathematical tools that we have, that if we want to maximize or minimize any function, all we need to do is differentiate that function with respect to the variable on which it depends and put that equal to 0. So, here we are already getting such a function over here for u, the potential energy. Derivative of the potential energy is 0. So, that basically means that at this particular time when we are talking about, or in this particular condition when the net force is 0, u, the potential energy, should either take its minimum value or its maximum value, or it should be a constant. Only then this derivative of u will be 0, right? Now, let us discuss all these three aspects of potential energy one by one. What do we mean by each of these values? Okay, and for that we will take up a certain example. So, case 1. Okay, let us say we have the case where the net force is 0, which means that minus of du by dr is 0. But when we differentiate this u function, the potential energy function, once again we get it to be positive, and d2u by dr squared, the double derivative of the potential energy function, this comes out to be greater than 0. Now, do we remember what is this condition for? If the first derivative of a function is 0, it is either a minima or a maxima or a constant. But if its double derivative is greater than 0, that means this function u is strictly a minima quantity. It is at its minimum value. Okay. So, if we can check the double derivative of the potential energy function, and if that comes out to be greater than 0 at the point of equilibrium, then we can say that that particular equilibrium is such that the potential energy is a minimum over there. Now, what does this mean physically? Let us take a figure to understand that. Let us say this is the ground level, and there is a small well which is being created here below the ground level, and this is once again the ground level here. So, this is ground, and there is a well which has been created like this, and there is a small ball which is at equilibrium at the bottom of the well. Okay. Now, do we all see that this point, this position where the ball right now is a position of equilibrium? The net force on the ball would be 0. Do you also see that if we consider the gravitational potential energy of the ball to be 0 at the ground level, then at this level the gravitational potential energy is even lesser than the potential energy at the ground. So, here the potential energy will be negative, right? It will be kind of minus mgh if this depth of the well from the ground level is h, right? Now, do we also see that here if you take this ball and shift it slightly from its equilibrium state, you take it slightly up and release it from there. If the ball is taken over here, let us say, and you release it from here, what will happen? Don't you think that the ball will tend to come back to its equilibrium position, right? So, taking the ball from its equilibrium position up to a certain displacement means you are increasing its potential energy, and the ball would try to come back to the lowest energy state by coming back to the equilibrium. Do you see, this is a kind of equilibrium that the ball will try to be always in. Whenever it is given a chance, it will try to come back to the same equilibrium state. So, such an equilibrium is called a stable equilibrium. For a stable equilibrium, a particle when it is displaced from its equilibrium position would always try to come back to the same equilibrium position by creating a restoring force. Okay. So, and in this case, as we have seen, the potential energy is a minimum here, as we can understand from the gravitational potential energy here also. Okay. So, this is the condition for the potential energy to be minimum and the equilibrium being stable equilibrium. Let us consider the second case now. Case 2 would be when for the same equilibrium state, for which basically means that the derivative of potential energy with respect to r is 0. Let us say now the double derivative of u with respect to r comes out to be less than 0. This is the case when u has to take a maximum value. Potential energy is maximum. How do we check for the condition? Let us take an example of, once again, this is the ground level, and let us say there is a small hill, a hill type body being created over the ground, and at the top of this hill there is a ball that is being placed right at the top. Let us say the hill has a height h. Do we understand that this position where the ball is kept is still an equilibrium position? The ball right now is just at rest, but do you see that if we just shift this ball from this equilibrium position slightly, if we shift it slightly over here, this ball will never try to go back to the equilibrium state, it will rather go away from the equilibrium state, it will try to go down, right, away from the top of the hill. Why has that happened? Because at the top of the hill, the gravitational potential energy of this ball was maximum, u is maximum here. If we consider the potential energy to be 0 at the ground level, then at a height h the potential energy will be mgh, which is greater than 0. And by the natural tendency, any body, any system would try to be in its state of minimum energy. So, right now since the ball has a high energy, it will try to lose all this potential energy and come down to the ground over here, so that it has a 0 potential energy. Okay? And in this case, we see that this equilibrium that we have just drawn here where the ball was becomes an unstable equilibrium. That how do we define an unstable equilibrium? An unstable equilibrium is the one from which if the particle is slightly displaced, the particle will not have a tendency to go back to the equilibrium state, it will rather try to move away from the equilibrium state. Okay? So, and at the equilibrium, now we know that the potential energy takes its maximum value. The third case could be that of what we call as a neutral equilibrium. What is a neutral equilibrium? It is still an equilibrium, that means the net force on the body is still 0, which means the derivative of the potential energy function is still 0, but this time the double derivative of the potential energy function is also 0. What does that mean? That means that the potential energy is a constant throughout, it does not change its value anywhere. An example for this could be, let us say the ground level, complete horizontal ground level, and there is a ball which is kept on the ground over here. This is the equilibrium state of the ball, right? Now, if we shift this ball from this state to let us say another state, let us say the ball is now kept over here, a new position. Can we say that at this position also the ball is at equilibrium and there is no change in the potential energy when we shifted the ball from the state A to the state B, the position A to the position B, right? So, we say that this is the case of neutral equilibrium. Neutral equilibrium means an equilibrium which does not create any change in the potential energy of the system when we shift it from the equilibrium. So, state A is also an equilibrium state, B is also an equilibrium state, and there is no change in the potential energy when we shift the system from state A to state B. Okay? That is a case of neutral equilibrium. So, the first two cases are more important here. In fact, you get questions directly based upon this to check whether a system is in unstable or unstable equilibrium, and this is the mathematics that you use there. Maybe we will take up an example here to understand this better. So, there is a question that says that the potential energy of a particle in a certain field or a force system has a form of U is equal to A by R squared minus B by R, where it is given that A and B are positive constants and the R value is the distance of the particle from the center of the field. Okay? We are supposed to find out the equilibrium position, find the equilibrium position. So, we are supposed to essentially find out the value of R for which the particle is in equilibrium, right? And we have to also examine the type of equilibrium and examine the type of equilibrium. So, what do? We first of all find out the equilibrium position itself. The potential energy function U is given to us. How do we find out the equilibrium? We first find out the force from the potential energy function, which we know is minus of du by dr, which means minus of d by dr of A by R squared minus B by R. Let us differentiate this, see that we will get minus of minus 2A by R cubed plus B by R squared. When we differentiate this with respect to R, this is what we will get. We can take an LCM over here and this will become minus of 2A plus BR divided by R cubed, and if we are looking for the condition of equilibrium, can we say that F should go to 0? That means this upper term here should go to 0. That means minus 2A plus BR should go to 0, which gives us the value of R as 2A by B. Let us call this R as R naught, the equilibrium position. This is the answer for the first part of the question, finding out the equilibrium position. So, R naught, which is 2A by B, is the position where the particle is in equilibrium. Now, we need to check what type of equilibrium is it. Is it a stable equilibrium or an unstable equilibrium? For that, what do? We find out d2u by dr squared and check whether it takes a positive value or a negative value at this r naught, at the equilibrium position, right? So, first we double differentiate the potential energy function. Double differentiation means you once again differentiate with respect to r the potential energy function. We already have du by dr with us. This is du by dr, we have already calculated it. So, this means we are supposed to do d by dr of minus 2a by r cubed plus b by r cubed. Let us do that. We will get plus 6a by r raised to the power 4 minus 3b by, not 3b, 2b, because we have an r squared. This is an r squared, not r cubed. This is squared here. So, this will be a 2b actually. This is a squared here. So, minus 2b by r cubed. This is what we have for d2u by dr squared, right? We can simplify this a little bit to get 6a minus 2br divided by r raised to the power 4, right? And now we can find out the value of this function d2u by dr squared at r is equal to r naught, at the equilibrium state. So, that we will get 6a minus 2b r naught by r naught raised to the power 4. Substitute the value of r naught here at the top to get 6a minus 2b into what is r naught? R naught is 2a by b. 2a by b whole divided by this, we can keep just like that itself, and see that this will be, b will cancel out and we will have a 4a. So, this will be 6a minus 4a, that is 2a by r naught raised to the power 4, which do we see is a positive value? R naught is positive and a is also positive. So, this value is coming out to be greater than 0. If d2u by dr squared is coming out to be greater than 0, can we say this implies that it is a stable equilibrium? Okay. So, all this we need to do in order to find out the type of equilibrium that we have for a system.